Good morning, students. Today, we are going to learn about Newton's law of cooling. We will also learn about the numerical method that we can apply along with the Newton's law through our experiment. I will explain to you during the process. Sarah, you will be using steel cup, and Liana, you will be using plastic cup. You may begin your experiment now.
Okay, doctor.
Boil your water until it reaches 100 degrees Celsius, and don't forget to take its temperature. I want both of you to record the temperature of the water every 1 minute once the thermometer reaches 100 degrees Celsius. Now, this is where you will be applying Newton's method. Take the step size as H equal to 1 and find the temperature of the water using the formula that I've written on the blackboard. After you have finished recording the temperature up till T equals to 10, please plot a graph to compare the results among both of you. As you can see, we can use Euler's method to measure the temperature of water during certain time intervals. Now, do you have any inquiries?
Doctor, why different cups give different results?
This is because every materials have their own thermal conductivity. The higher the thermal conductivity, the lesser the time taken for the cup to lose the heat to its surrounding, and thus affecting the temperature of the water. So, that means the thermal conductivity can affect the water temperature, which will then affecting our results. That is correct. The thermal conductivity is the constant K in the formula of Newton's law of cooling. Therefore, it will affect the temperature. Now, based on our experiment, give me an example of real-life problem that we can apply Euler's method to our daily lives.
I think we can use Euler's method to estimate the time taken for ice to melt. For example, we can know at what time the ice fully melts or how long it will take for the ice to fully change its state to liquid.
Good job, Sarah. However, Euler's method is just a basic step in numerical method. The larger the step size, the larger the error because it will diverge from its exact solution. Doctor, can I ask you something? How to calculate the error? Thank you for asking, Yana. The formula to calculate the error is this. take the absolute value of the difference between the exact value and the approximate value, and we divide it by the exact value. We usually calculate the error in percentage, so times it with 100%. Now, before I end my class today, I will give both of you a question on Euler's method with different step size as a homework, so that you can see the differences. And please submit to me during the next class. And if you have any questions, you can ask me later. Thank you.
So this is our homework. We need to solve the following differential equation by using Euler's method, given that y0 is equals to 1. We need to find y0.5 by using h is equals to 0.1 and 0.05. This is the solution for the step size h is equals to 0.1. We start at the initial value x0 0 and y0 1 and calculate the value of the derivative at this point. We have dy dx is equals to -2. We substitute our starting point and the derivative is just found to obtain the next point along. Here is where we will use Euler's method and we will get 0.8. Now, we need to calculate the value of the derivative at this new point, 0.1 and 0.8. The derivative we will get is -1.5992. Once again, we substitute our current point and the derivative is just found to obtain the next point along. Our y0.2 will be 0.6401. To show it once again, we calculate the derivative and we will get -1.2748. And substitute into the Euler's method, and we will get our y0.3 is equals to 0.5126. To summarize all the values of x, y, and dy dx, we put them into a table. This is the solution for the step size h is equals to 0.05. As usual, substitute the value of x0 and y0 into the derivative and we will get -2. We then calculate our first iteration by substituting into the Euler's method y of x0 plus h times f of x0 and y0 and we will get 0.9. Next, substitute x1 is equals to 0.05 and y1 is equals to 0.9 from the previous iteration into the derivative to get -1.7999. Our second iteration will then give result to 0.81. Again, substituting 0.81 into the derivative, we will get -1.6192. After substituting the value of the derivative in the Euler's method, our y0.15 is equals to 0.729. So this is the table of x, y, and dy dx for the step size h is equals to 0.05.
So, here is the graph to compare the value between h equal to 0.1 and h equal to 0.05 with exact solution. As we can see, the graph for h equal to 0.1 diverges faster than h equal to 0.05. The value for h equal to 0.05 diverges only a little from the exact solution. Hence, we can conclude that the smaller the step size, the
more accurate the solution is. However, the error is getting worse as x increases. Therefore, Euler's method is a nice method for approximating fairly nice solutions that do not change rapidly.